Hello folks. Well, this time I want to talk about profiling your code. This is essentially running analysis tools on your program as it runs to see how long it takes to run, to see how long different parts of the program take to run, to see how much memory you're using. Right? We've often got general ideas on how long or how fast we expect it to be or how much of a memory hog we expect it to be. But it really helps to have some actual analysis where we can back it up and say, yeah, I ran it on these cases, and here are measurements on how long it actually took. So for today, I want to take a look at profiling in general, talk about some of the theory behind it, and then in our next session, we'll get into looking at some specific tools for code profiling, both memory use and CPU utilization. All right. So again, usually when we write the code, we've got some kind of an idea in the back of our mind of how efficient it is or isn't in terms of how long it's going to take to run and how much memory it's likely to use, at least whether it's, you know, kind of fast, kind of okay, not so good, or really slow, and some mental idea of what this is like. And it might be the case that we've gone through and done an analysis of the complexity of the algorithms that we're using, and we've actually got some idea in the back of our mind saying, okay, well, I expect this to run in logarithmic time compared to how big the data set is, or linear time, or exponential time, or whatever it might be. We've got some sort of theoretical analysis of how long we think these things are going to take. But again, our theories aren't always correct. So it helps to have experimental validation, to have data that we can actually point at and say, here's some real analysis on how long this thing took to run. So code profilers are tools that help us in doing this, where they actually go through and measure how much time the program took to run, and not only that, but how much time different functions or methods within it took to run. How much time did we spend in this function as the program ran? And similar ideas for memory, you know, how much memory was consumed by it, how much memory was consumed during this phase or at this point. So the way these things are going to work, there's, I guess, two broad styles of code profiler. So one of them actually takes the machine code for your program and produces a different version. Well, actually, it works from your source code, but produces a different version of the machine code for your program in which it actually inserts extra code that lets it do the profiling. So you wind up recompiling your code, and it inserts maybe something at the start and the end of every function call. So when your function is called, it starts a little timer going, and when the function completes, it stops that timer, and it can measure exactly, you know, how much time was spent in that function. And so it would automatically go through, and for every one of your functions and every one of your methods, insert just this little extra, you know, check what time this started, check what time it stopped. And then what the profilers will usually do is have a data file that they're keeping someplace, and as the run of the program goes on, the profiler is going to figure out, okay, how much time did we spend in each of those different functions, and record it in this log file. How many times was the function called? How long did we spend in it? Right? Cumulative across all the different calls to it. Same idea for the memory idea, where it's going to say, okay, well, let's insert code to actually check how much memory we're using. Or maybe each time a memory allocation is done, we'll stick in a little chunk of code that says, okay, let's check how much we allocated and record that, again, in a log file someplace. And every time there's a deallocation, check, okay, well, how much did we deallocate? And take a look at that. So the code injection is probably the most common approach. There is an alternative. There are profilers that work by sampling, where instead of injecting new code into your program, what they do is, you know, every so many milliseconds or microseconds, they interrupt your program and just see which function were we in when we interrupted it? How much memory were we using when we interrupted it? And so you just get this statistical sampling of where you were, which functions you landed in how many times. So if you landed in if you did 1,000 samples, and you landed in one function 100 times, then you're going to say, okay, well, I'm going to estimate that I spent 10% of my time in that function. It's not an exact measurement, but it's reasonable sampling, and it doesn't wind up altering your object code to perform. All right. So again, we've got these two styles, injection or samplers. The injections require us to recompile the program, and when we're doing that, we'll have to give the compiler a special flag, basically saying, okay, I need you to generate this extra information. And again, it's going to be along the lines of generating some kind of a, maybe take a snapshot of the time when we enter the function and a snapshot when we leave the function, and log that data. And then there's got to be some kind of reporting process afterwards that reads the data file, the log file, and generates for the user some kind of human readable summary of all this information. You know, it goes through all these thousands of different timestamps and says, okay, well, here's a summary of how much time we spent in each function, how often it was called, etc. And then for the sampling profilers, one of the big catches with those is because it's got to interrupt the program periodically, that's typically an operating system level privilege, which you often don't have as the user or as a user of the system. So, program gets run in a special mode. We have these interrupts generated at fixed intervals, and at each one of these, it checks which function or which method we're in, or checks how much memory we're currently using, and builds up this sort of log of snapshots that we can analyze after the program completes to generate data on, you know, what percentage of the time did we spend in each of the different functions, how much memory was in use at each of the different snapshots. So again, they both have advantages and disadvantages, right? The injection style actually inserts extra code into your program before compiling it and running it. So that is going to change the runtime behavior, right? The code isn't exactly the same as it was. Whereas the sampling style requires that you have these special privileges that you be able to interrupt the system at, you know, all of your different snapshot points. And it's giving a statistical analysis, kind of a probabilistic measure, not an exact measurement of the runtime spent in each of the different functions. Now, if we want to be able to use our profiling information, then it's not usually adequate to just run the program once on one sample data set and say, okay, there we go, it took this long, there, I'm done, I'm happy. What we want to do is to be able to look at trends in how our program behaves on different data sets so that we can do things like, with some level of confidence, predict how long it's going to take on a data set of some new size, right? So that we can make reasonable predictions about real-world situations for our program. So we need enough different data sets of different sizes and different kinds of data to be able to make realistic projections. So sorting programs are always an easy one to use. You know, if we've got a sorting program and we expect to be using it on, you know, data sets of size 10,000, then I might try it on sizes 1,000, 2,000, 3,000, etc., 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 up to, you know, 20,000 or 30,000 or something along those lines. So you get this reasonable cross-section. I might try it on sorted data. You know, how does it perform if the data is already sorted? How does it perform if the data was actually backwards to what we ordered? How well does it perform if the data is randomly ordered? So you're trying to gather a collection of profiles of your program's behavior so that you can project what it's going to do in other situations. So you're focused on trying to get sort of real life, as close to real life data sets as you can get, good representative data sets. Let's see, just to backtrack a bit in terms of the memory profiling, similar idea. We want to look at how much memory the program uses. Again, similar idea, we're just inserting code at different points to check how much memory is in use. Or to go through and look at every time there's an allocation or a deallocation, take a look at how much space that particular allocation is generating or how much it's freeing. Similar idea, just focused on memory, not runtime. And again, just to bounce back and forth here, I think I've got my slides out of order. We want to go through and gather reasonable information for our profiling process. So this is back to the sort of sampling idea that I was talking about earlier. We're going to gather and plot information from a whole slew of different data sets. You know, if we expect our sorting program is going to be used on a file that's 10,000, 50,000 lines long, we want to start with files that are smaller than that and go to files that are much bigger than that. Right? So you might pick 20 different sizes of file. And for each of them, we might look at 3 different styles of content. Right? Content where it's already sorted, content where it's actually backwards. Right? That's the worst case scenario for many sorting algorithms. Sorted, we might want to see if it performs well if we give it data that's nearly sorted already, or if it still is just as slow as it is on other data. We might look at randomly ordered data if we expect that to be the case, or we might look at nearly sorted data. If we expect the runtime situation to actually be using data that's nearly sorted, but it's going to have a few new things injected every now and then that might be out of order, then that might be the kind of data set we want to test it on. Right? So you're trying to look to get a reasonable cross-section of behavior in realistic situations. So if we were to take this, right, we've got say 20 different sizes of test case and 3 different styles for each, so we've got 60 different types of test. And what we might do is run, you know, 5 or 10 tests on each of those, so we wind up with something like 300 tests overall. And then you wind up plotting the behavior on a graph, so you can look at your CPU time, you know, plot the behavior for sorted as one line, plot the behavior for reverse sorted as another line, plot the behavior for randomly ordered as another line, and just take a look at where this trends. And you can start again getting a feel for, does this appear to be, you know, logarithmic, linear, squared in terms of your data set size, is it exponential? But you can get some a reasonable basis for extrapolating and predicting what kind of performance you're going to get on other data sets. And that's the idea here. So that's the idea for profiling our programs. What we'll take a look at in the next couple of sessions is the use of gprof, which is one profiler for analyzing the runtime. And we'll take another look at valgrind, which we can use to analyze both runtime and the memory use. So we'll come back and tackle those next time.